Hi everyone, thank you for having me today, and thank you for this opportunity to be able to share my knowledge about using some deterministic approach to enhance code architecture and the review. I will be based on some mathematical concept, but don't worry. When you see the word mathematical isn't hard, I will try to make things some bit funny. So we will learn many things together, and the subject isn't hard, but it is very, very beneficial. So let's start by introducing myself. For the person who don't know me, I'm Khal, and I'm a senior software engineering. I have written many books and write many articles, and I do many conferences and meetup. I love everything about software performance. I have a deep knowledge on software design and architecture. And I love also to introduce mathematical concepts in our daily way to do software, since software is a deterministic science discipline. And the today talk is about this, about how to use some mathematical approach in order to enhance our architecture, our code, our review, based on some mathematical concepts like graph theory, for example, category theory, and Lambda Calculus. We will see together how this concept will help us. So, for the content, what we will see together, we will start by understanding the KU in our application, and then we will try to use graph theory to modelize and enhance our architecture, how to have a deterministic approach to say that our software is modular or not. Then I will use category theory in order to redefine data and relationship, since in JavaScript code, poorly, this relationship is not very well understood and is not very well done. And then we will use Lambda Calculus in order to push and enhance more our code to enable some performance feature like lazy evaluation, like memorization, and high-order function. So let's start by understanding the KU. How does a bad code affect performance and debugging and maintainability? So the first KU we will encounter when we write a JavaScript code is that JavaScript is a dynamic language, is interpreted, is just-in-time, and it is single-threaded. And all of this characteristic impact the performance of our application. What I mean by this that in the client side, we pay for what we code. If we deliver a performant code and a good modular application, this will have a good impact on the used resource. And the inverse, if we deliver a non-modular application, spaghetti code, we will pay this in the client. Since JavaScript, it is interpreted, it is just in time, we don't have compilation, what we write is what is delivered, what is executed. Then, the other part of KU is the JavaScript open mind. JavaScript will look at if we do mutability, it's fine, it works. If we do side effect, it's fine, it works. If we have KU code, it works. If we have callback hell, if we have long function, if we have function with many parameters, if we have function with many responsibility, with many nested statements, for JavaScript, never mind, everything is good, it is optimistic, it continues to execute. Then, the other part of the KO is the developer unique practice. Yes, as a software developer and as a senior software developer and the architect, I pass I think, 18% of my time reviewing code, enhancing code, debugging, supporting, and trying to make the developer workflow more efficient and more performant. So I daily encounter this unique practice, hoping that it works, trying stuff until it works, and temporary workaround, and I have function inside function, inside function, inside function. So, as an architect also, we have some schizophrenia. Since we don't know what is the most suitable architecture to use, and we encounter many design patterns. Somebody, they say in this part, I will use, for example, facade design pattern. I think that hexagonal architecture is the most suitable for our case, but who's know? Where is the truth? What is the best architecture for our case? Then the change nightmare. Each time we change a small part of code, we will create many other bugs. And this why, because of our unique practice, in order sometimes we don't try to understand the problem and to find the efficient solution for our problem, but we try to make working out, trying stuff until they work. And the result of this is having a bad code. And this is me every day. When I review code, I cry, please. And each time I encounter an issue, I try to find an efficient solution to not again encounter the same issue over the time. And that's why, so if we resume the challenge of a growing React code base, so we will be split between maintainability and the growing code base. We will split between how to have a performant code and in the same time have to have a maintainable code. And we are split between which is the good approach I should use that can help me to equilibrate performance and good code and good maintainability. And we should not forget that poor code will cause poor performance, poor maintainability, and this will cause a high development cost. Everything is related. If we code bad code, this will have expensive cost for maintainability and for performance. So that's why we need another approach. We need an effective, objective, and deterministic guideline in order to architecture our code, in order to review, in order to code. What I want is, when I ask, is this the best way to modularity and is the best way for loosely coupling, I should have only one response and not many patterns, many factors to take into account and to apply. So, based on numerous stages and research, and getting inspiration from literature and from engineering inspiration, I found that we can use many mathematical aspects to control and to assess our software architecture by viewing our software as a network of file, network of package, and once we modularize our software as a network of connection, we can find and apply all graph theory, for example, in order to assess good community, good modularity. We will see this together. And also from mathematical engineering inspiration, I found that we have a magical concept that is the essence behind the composition. This concept is based on the category theory, and it states that we cannot have a complex function, we cannot have a complex domain, but each complex domain is the composition of many small other domains. It is the first step for the composition. So to very well understand my goal is to find a deterministic guideline. How can I be sure and control over the time the evolution of my code base, and I am sure that what I'm trying to do and to add and to evaluate my software, I evaluate in the right direction. Based on the different research and the different engineering inspiration, I share with you my way of doing code, of architecture thing. I call this a soft mathematical framework. It is not soft because it is not very hard. It is a logical way to structure our code, to write code. And when we are in the mathematical domain, we can benefit from many advantages, like, for example, lazy evaluation. Lazy evaluation enables many things behind, like having lazy stream, lazy array, using category theory, for example, help us to have functor, like help us to have monad, and all this feature help us to having, instead of mutation, for example, having transformation. Instead of having big function, we will have a mapping of many small functions. So my soft mathematical framework is based on graph theory that work in the architecture level in order to have and to assess modularity and loosely coupling. Then we will work inside function in order to correct bad smell of function, like mutability, like having big function, like having functions that accept many parameters. Then we will use Lambda Calculus in order to enable feature like lazy evaluation and memorization. So the goal is to move from, when I ask something about design and code, we move from the answer of yes and no, the two, maybe, to having a deterministic answer. Is it modular? I need to have a single answer, yes or no, and not yes and no in the same time. So let's explore, and let's start with how can I exploit graph theory in order to analyze and optimize our project structure and architecture. So the first thing about graph theory, the first step is to model software. Modeling software using a graph is to consider that each file is a node and each import is an edge. It is very important since this modelizes file interaction. If file A import file B, then we will have a node, file A, and we have node file B and an edge from A to B. This is very important since this will give us a modularization, an abstract modularization of how all files inside my project interact together. And once I modelize my structure and file using graph theory, I enter in the graph domain, and this will help me to apply many graph theory, formula, and concept. For example, what can I apply? I can easily detect cycle detection. We know that cyclic dependency are harmful for bundler and for compiler, since they can create an infinite loop, and an infinite loop inside JavaScript will create a Stack Overflow. And this can be also harmful to bundler, since they cannot very well split the final bundle into the correct chunk. Since file A import B and B import A, we have a cycle, so we do not know. As a bundler, I don't know if I should put A with the bundle, with the chunk of the B part, or it should be with the B part. So detecting cycle dependency is something, it is a very important thing to avoid indeterministic behavior at runtime, Stack Overflow, and indeterministic bundling when we run, for example, Vite or Webpack. So to detect the cycle, it is simple. We can use, for example, DFS algorithm, depth search first algorithm, to detect that, for example, here I modelized my workspace, all my file interaction, which file import which, and I easily identify that I have a cyclic dependency. Then what can I do more? I can detect community. This is the magic, and this is the very important part of using graph. I always, when I ask what is the best way to organize my architecture, the first thing I do is to ask my colleague what is the best approach. And as we see at the beginning, every person, each one have its own proposition, its own solution to the same problem. But which one is the correct and the good way to organize my structure? So for this, I try to find a deterministic way to organize my structure. And after modelizing it in a graph, I can apply community detection algorithm. This community detection algorithm will detect what is the best way to split my project based on file interaction. What is a community? As a definition, a community is a group of files that are highly cohesive and loosely coupled with the external dependency. And that's what we need to do to know when we modelize and in the design phase. So we want to know, and we want to decompose our file, our module, in a way that we maximize cohesion and minimize coupling with external part. So I use the method of Lovin. The Lovin method is a way to detect community inside a cluster, inside a big network. So the result of applying this For example, I analyzed my workspace, and it gives me many community based on which file import which file use each file. It's like how bundler do think. It's something that will be helpful also for bundler in order to create the correct chunk. So that's why I say that code, the way how we write, impacts the performance. So based on this, I found some community based on file interaction. For example, based on different import, I have to do a module or community 0 and the community 1 and community 2, and I have a file that is not used. It is a deterministic way to find a group of files to create a package that ensure that it is highly cohesive internally and loosely coupled externally. Then I can also use other approach of graph theory in order to calculate the centrality of a file. For example, here we can calculate in degree centrality, which means how many files depend on a specific file. So if we have a value of 0, this means that this file is isolated. If we have between 1 and 3, so we have a low dependency, and this is a representation of what we call the afferent coupling, the incoming coupling. Then we can also calculate the out degree of centrality that measure our package or our file depend on how many other modules. So we calculate the incoming edge and we calculate the outgoing edge, and finally we can sum them to calculate the centrality. So what we can do with centrality? With centrality we can calculate the instability index. What does it mean, instability index? This means that what happens if I change a file? What is the degree of instability? What is the level of software disorder, or what we call software entropy, that we will create? And also based on degree of centrality, I can find unused file. Unused files are a dead code, so it should be removed. Then I can use them to prioritize test coverage. File with a high level of degree of centrality are the file where I should and I must have a unit test to cover it, since it is a touchy file. It depends on many files, and many files depend on it. I have a deterministic way to say that this file needs a unit test, and this file is not very important at this time to write a unit test for it. So we don't have any more excuse to not write unit test. Then we have also other indicators like density and sparsity. So if density measures how interconnected the project graph is. Dense project is the project what we call spaghetti code. It is very dense, so we cannot understand the interaction between files. Sparse code, or the opposite, indicate that this project is a small project, or it is well modularized. For example, based on density, I move from this to this. So when I see that I have a part that is very dense, I will prioritize this part for refactoring. This part needs a refactor. This part needs to be more modularized. So based on this project cartography, I can guide refactoring, unit tests, assess modularity, and having a global way to assess the project quality. Then, so this is a deterministic approach to guide refactoring. So in the team, we all see the report generated after the graph analysis metric and after graph modelization in order to see which part deterministically need to be refactored, need to be reviewed, and need to be covered with unit tests. To implement this, you can use, for example, merge in order to extract the project dependency as a graph based on file and import. You can use merge also to detect circular dependency, and you can use npm package graphology in order to compute graph-based metric. And you can use also or inspire from my open source tool, CodeHealthMeter, that integrate all this tool in order to have all the metric I need. So at this level, I find a deterministic way to organize my project structure. So at the future, when someone asks me, is it good? Is it modular? I will say it depends on the graph analysis, and it is an objective and deterministic way to assess the quality of organization. Now we will go forward and we will correct now the relationship data and relationship, since in JavaScript we don't use correctly or implement correctly the relationship or the function that work on data. A software at the end is an input data that is changed to another output data. And this is the relationship. In JavaScript, the majority of code describe this change as a mutation, which is not good, since mutation create indeterministic behavior and make testing very hard. So using category theory, we will try to redefine the relationship that work on the input data. How we will do this? What the category theory give to us? Category theory redefine the relationship between the object or the data on where we will work. Object can be, for example, sets or any type of data, and the change from the input to the output is called a morphism. And the morphism is a special change. A morphism is a special change that do only transformation. And the beauty is that it preserves the structure. So we do transformation and we preserve the structure. What we gain from this? We gain consistency, we gain deterministic behavior, and also in category theory, say that if we have a complex morphism, if we have a complex transformation, We cannot write this complex transformation. We should make composition. Like in math, for example, if we have a complex expression, we internally at our mind, what we will do? We will try to decompose this operation. The same way apply to software. When we have a complex function, we should decompose it into small transformation. It is important to use the word transformation rather than the word mutation, since mutation brings unpredictable behavior at runtime. On the other side, transformation preserves structure and are a pure transformation. So what we gain from category theory, it gives us transformation, not mutation. We don't have a mutable code. Or if we have a mutable code, we will try to locate it in a single part, in a separated part. And I will show you how we can work with mutable code in a safe way, in a deterministic way. Category theory will help us to preserve the structure. If we give as input an array, the output should be always an array. A purity, we are not allowed to change the input. Since it is a transformation, we should do only transformation. We are not allowed to change the input. And an interesting feature which is the composition. How to apply this? The first way to apply this is to use what we call functor. For example, JS array are a functor, since they implement a special function that is called map. And map, what map do? Map will do transformation. Map create a new array rather than mutating the original array. And it is very important for predictability to have a deterministic execution at runtime. So functor are an abstract way to work with data without mutation, using only transformation, and they are a special relationship that implement a magic function that is called map. So we map from transformation to another transformation, and we are composing transformation. And functor are a way also to preserve the shape, to preserve the context, like category morphism, where we preserve the structure. Some practical example of applying category theory and using functor. As you can see here, I started my review with a big function. This big function do many things. So in our guideline, we say that we must apply, we must adhere to category theory principle. What are the category theory principle? The most important principle is the composition. So we will start by splitting a big morphism into a small morphism. So we will start to split the big function into many small functions. Then we will implement a functor. What is a functor? Our final output should be the combination of all this transformation. So I want to combine all this morphism and have my final output without mutation, with preserving the structure, and with all capability of homomorphism. So what I do is a magic structure that I called CanApply. CanApply, it will map through the different functions. And when a function, for example, creates a side effect, what is a side effect? A side effect is, for example, an exception. In Functor, we are not allowed to make a side effect. So if we have an exception, we don't continue to execute each map, but we will directly jump to get value. It is a more clear way to chain transformation, to have reusable small function than having a big function that contain all of things. And if, for example, we want to reuse format output, for example, since we don't create small part, we will each time repeat the code. This is the good impact of using composition. So the CanApply is a reusable structure. We can implement it like this. We can use Functor, for example, for safe process. I create my try, and it will try to transform everything. And if I have an issue, I will jump into the catch. This helped me to what this gives me. It gives me the way that when I want to do transformation, I will say that all my transformation will be done in a correct way. So I will never have an exception. And when I have an exception, I will try to catch it in the default path. So we separate the implementation from the functional part I want to do. I have write a reusable part that will apply a function only if the value is defined, and I will reuse all this CanApply each time I want to chain many transformations in a safe way. I can also make a functor for asynchronous processing. For example, I can create a task that wrap the side effect, and I can chain the different transformation once I have the result. So that help me and enhance my code in order to repeat and avoid me to repeat each time the error check. But functor have a limit, so we cannot return a functor from a functor, since they create a deep structure. And here, monad come into play. Each monad is a functor, but not each functor is a monad. A monad is an augmented version of a functor. Promise, for example, promise then catch is a monad. JS array is a function, is a functor. Promise is a monad. A monad is an augmented version of functor that can give us the way to have a flat structure, like, for example, having an array that contains another array. So we need to have flat map in order to work with the element inside the different subarray. I can make monad, I can use monad for form validation, like a result in Rust, for example. I can use monad to have two-way, a way for the good, the OK, and a way for to handle the error. I can use monad to handle asynchronous effect, and I can also make optional values like what we have, for example, in Java, or like what we have in Rust. I can make pattern matching in order to replace the nested structure of switch, for example, or of nested if. I can use lances, for example, to updating nested structure without mutating an object. Functor, monad, lances are all a mathematical concept that exist inside category theory. The application of this concept gives us this code, which is deterministic, which is without side effect, as each mathematical function, as any mathematical function. We cannot have a mathematical function that do, for example, mutation. It is impossible. We have always transformation. We cannot have mutation. We preserve always the input. And I can also make transducer. How transducers are important, since the map, filter, and reduce of JavaScript should transform all. If I have, for example, map, filter, reduce, we should map everything, then reduce then filter everything, then reduce everything. Sometimes I don't need all the data. I need, for example, only a small subset. If I have, for example, in the front end, I have a load more or pagination. So I need to transform 10 by 10. I don't need to transform all the data. So using JS native implementation, this is not possible. If we have 100 data, this data will be fully transformed. So we use transducer in order to avoid intermediate array, and in each iteration, we process only what we need. For example, here I process only necessary event. Here I process only necessary user. I don't process all the data. I work when I need, I process. So if we recap, category theory gives us the pattern like functor. Functor applied transformation while preserving structure. This is very important. I can't give confidence to my code if my code do mutation. It must be predictable. It must be deterministic in order to deliver my code. When I deliver my code, I must be sure that it will not cause side effect. So everything must be visible and deterministic. Monad, in order to change side effect, pattern matching, lances, and transducer. And the benefits: immutability, composability, predictability, and testability. You will find all the implementation in this in my repo. And finally, the Lambda Calculus, they enable many concepts like carrying, lazy evaluation, memoization, and high-order function. For example, once we have a pure domain, once we have a predictable domain, this enables us to make many enhancements on performance. For example, using carrying for reusable validator. Then higher order function. For example, these are my easy implementation of higher order function. I compose function, throttle depends, to check if a function is executed only one time, having an approach of when I have condition, then I execute treatment. And the interesting thing about high order function, so all this utils function are created once and reusable every time I need to compose stuff. Then I can also make lazy evaluation. Lazy evaluation is interesting when I want to handle stuff at the need. I can make lazy stream instead of having an array that handle all data. I can make memoization in order to enhance recursivity, and I can make what we call trampoline to enhance recursive JS, since JS isn't TCU, which means isn't tail call optimized. The conclusion. So, what we take away, what I shared with you is having a deterministic way to apply mathematical concept in order to have a good code like the deterministic approach of mathematical concept. So when they now ask me, is it modular? I will say, look at the graph theory metric. When we say which part need to be refactored, I say graph theory metric. Which architecture style is most suitable for me? I will say, look at the graph metric and decide which style you will use for your organization. Is it composable, predictable? If you use category pattern, then it was. How to optimize using Lambda Calculus techniques. And never forget, Khal is software engineering that say that computer programming is an exact science. We should be able to define and determine everything from the code we write. From the code we write, we can identify a metric, we can predict maintainability, we can predict performance, we can do everything since it is an exact science. Isn't I will try the thing and until it works. No, it is an exact science. And thank you.